Okay, welcome to the analysis for vector addition. That's the lab where you went out as Lopes migrating around the campus, uh, marching off 6 bearings, determining what your pace was, and finally coming to your destination, which you'll soon learn, unless your instructor has already told you how well you did. Anyway, I usually keep that a little bit secret until the end. But anyway, we're going to go over the various parts of the lab that you need to be aware of as you write it up. And if I look down, it's because I'm looking at my document right here. So you should be seeing right now the Vector Addition Lab 5. The objective and the hypothesis were given to you, so you don't have to do anything there. Be sure and read them because you're going to have to answer those statements later in the lab at the end, in the conclusion and the hypothesis statement. So as you can see next, the controls, pretty simple. You could say true north, is theta. By the way, theta is the angle. Degrees is the unit. So you don't write theta degrees. You write theta, and then it's like equal to 50 degrees. But it's not theta degrees. Anyway, the only one that really needs to be there is the Lopes migration map. And maybe your elevation, but we do live in the valley, so things are pretty flat. The independent variable are the individual polar, and you'll also be calculating the Cartesian coordinates, so you can throw those in as well. And you can see those right there on the sheet. I hope you can. And the resultant vector, polar vector, that's the ultimate destination, is to determine where that set of vectors dropped you off. So that's your dependent variable, the resultant vector that you get by following a particular Lopes migratory path. All right, so the design table down below would have Ri and theta I. There's 6 of them. The corresponding Cartesian coordinates, xi and yi. I chose capital X, capital Y, since R is capitalized, so we might as well keep everything capitalized, make it look really uniform. And then the resultant is just a single number. For R, the magnitude of your vector addition, your total displacement, and then the angle that it makes with north. Now remember, you're working true north. So all the angles are all the components are determined relative to true north being 0 degrees. Anyway, the materials you can figure out, but they're right there. And next in your procedures, don't forget to give the equations that you need to use to analyze to determine your coordinates. Actually, to work around a building, you may want to discuss that in your procedures. You definitely need to talk about your pace and how you determine that. All right, but usually with the trig, they put them all together like you see here on the page. All right, going down to the data, 2 data tables. One is the theoretical bearings, and then the other one will be your measured bearings. Okay, and I met with a group today, and they gave me their data. So there are 6 bearings, like 105 at 90 degrees, 275 at 44 degrees, and so on. I'll just show you how to work that out in Excel so that you get those values. Lastly, in the analysis, which is the most important part of the lab, is you need to plot your bearings on the Lopes map that you'll find at the end of the document. So this is Lopes 2, and by the way, you should key the color. So you should key like the blue here. Let's see. I believe the blue was the measured bearings, and the orange yellow line was the theoretical bearing. So be sure and color code that somewhere. Also, you need to figure out the scale for the map, and I'm going to do that next. So I'm going to bring up my Google Maps for the campus, and up here near the top, you can see Missouri Avenue. Let me get this out of here. Oh my gosh. Okay, so up here at the top, you can see Missouri Avenue. I'm going to pull everything down a little bit because that tag up there is getting in the way. Well, if you drop a line, you just right click, find the place you want to put the line. I like to go right at the corner, which you can't really see the corner because it's a rounded corner. As you know, whenever you get to a corner, it's not like ding ding. It's always rounded like that. Anyway, I'm going to measure the distance. So I click on that spot, measure the distance, and it puts a white little circle there. And then I go to where I want it. I'm going to go to the pathway all the way on the east side of the campus along Missouri there. And that's looking pretty flat right there. And then you can read the value down below. So it says it's a total of 781.79 meters. That's 5 significant figures. But when you work on your map, you're only going to have like 3 significant figures on your map. Now, if you worked entirely in Google Maps, you would get a little bit more precision. But as all of our labs go, 3 significant figures is good enough. So anyway, I'm going to go back to the map. And if you figure that out, so that number, remember what that number was? I already forgot it. So here, let me bring it back. So it was 781.79 meters. I should write that down. I'll probably have to come back to it. All right. So now you got to figure out how many inches that is. So you go up to Insert and you choose Shapes. And you get yourself a nice line and you go up there at the top and pull it all the way across that exact same distance. And I will color it a brighter color so you can easily see it there. I'm looking for my color right here. So anyway, Format Shape. I'll go over here and I'll pick bright yellow right there. So you can see that bright yellow line. You don't need a vector arrow on that one. So I'm just going to turn that off. But anyway, up in the upper right-hand corner, or if you don't see it in the upper right-hand corner, there is a box that tells you what the dimensions X and Y for any line you draw. So if it's not there, you just click on Format Shape and it'll appear. And if it's not perfectly horizontal, you can just set it to, like the vertical should be 0 because Missouri Avenue is horizontal on the map. And I get 6.30 inches right there, 3 sig figs. And so now that 780 whatever it was meters is the same as 6.30 inches. And so we're interested in the inches. So we should divide both sides by 6.3 and I get about 125 meters per inch, 1.00 inch. All right. So then I go ahead and I take that map that I went outside and I find those places on this map and then I draw out all my vectors. Use the same color, put an arrow on the end, remember tail to nose, tail to nose. Make the vectors pretty wide. These guys right here are 3 points. Okay, you can clearly see them. Now they used orange here and then they ended up with a nice yellow line. That's kind of orange-ishy. And then they went with the light blue and then finished with a dark blue. All right, and if there was a nice key down below, I would know which is which. Right now, I'm guessing, I'm pretty sure that the blue was the one they marched out, okay? That's the one they walked. So that would be their measured bearing. Now you already have the original theoretical bearings. Now you need to write down all the X and Y coordinates for the bearings you walked out and then transfer that to your Excel spreadsheet. Yeah, get that over your spreadsheet. So now let's go over to that spreadsheet and show you what you would do. Okay, so first of all, this is the theoretical. I'll just write Theo there so we remember what that is. And those are original bearings. Now remember, 0 degrees is north. So if you want a y coordinate, you need to use a cosine. Okay, so if your angle was like this and you want that piece, okay, remember you're measuring the angle off north. You need cosine for that. Sine is going to give you the x. So if you look up here in the top, you can see I got C9, which is the R1 vector, and then I type times, which is an asterisk, and then sine, and then the sine has got to be in radians. So I push radians, open parentheses, and then I click on D3. By the way, when you click on the cell that's got the data you want to calculate with, it'll put the cell right in the formula. So you can see C9 star sine radians D9. And I get that number right there. And then all you have to do is click on the corner and it will fill it in right to the bottom. Now you can worry about siggies now. We can assume that your angles are good to a degree. So like these two guys should really be just two significant figures, but you don't need to round off to the to the ones place. That's okay. The other ones are round right off to the ones place. You know, like the 105, you should really make 110, but that's all right. You have to go in there and just physically change it. Now the other ones are all 3 siggies, so that all looks good. So remember, I use sine for x, and then for y, I've got cosine, and I double click on the corner. I missed it. Ooh. All right, hang on 1 second there. I got to back up a little bit. Enter. And good, I didn't lose anything. So D9, I did lose one. This is supposed to be C9. So C9 and then cosine D9. All right, cosine radians D9. All right, so I get 0, which is perfectly horizontal bearing. And there's my final result. And I can round those off to siggies, 3 siggies. And then I need to add those up because, you know, once you get the Cartesian coordinates, you get the sum of those coordinates, then you square them, take the square root, you get r, and then for theta, you have to take the inverse tan. This time, remember, the inverse tan is going to be x over y, not y over x. By the way, there's a really nice sum button up here, so you can just sum these things up. So you click on the sum, and then it asks you, oh, it already knew. See, it already knew what I wanted. And so the sum was 5 meters. Wow. And then the other one is, let's see what we get. We do that. And enter. I get 241.1. All right, that's pretty weird. Let me go check the map just for fun. That makes good sense. That makes very good sense. Okay. So that's the result right there. Again, when you add them all up, they should just be to the nearest meter. And then, you know, you got to do the square, the square root of the sum of the squares. It's really nice. Excel's got a SQRT for square root. And then you just click on the x value and go caret dos. And then plus, hit the y variable and put caret 2 and close the parentheses, and that'll give you the square root, which is 242, which notice it's exactly the same value as y because x is so dang small. And then to get the angle, you got to go equals a tan. Now, there's no angle. Remember, it's going to give you an angle, so you want it in degrees. So what you do is you go radians on the outside equals radians. Oops. And let me try that again. Radians and open parentheses. And then you put the a tan in there and then open parentheses. And remember, we want to go x divided by y. All right. And then we go and close it up twice. And I get how many degrees? I get, oh wait, it did not change it into oh, right. Look at that, 0 degrees. That makes total sense. 0 degrees. That is the value. Actually, you could have 3.6 for that. What was that value again? Let's have a little, 0.00. Yeah, it's 0. So put 0.00 just to let you know that we did that. All right, now, from all of your measurements on your map in inches, those would go over here. Notice it's xi in inches, yi in inches. I do not want to see that data in your lab report. Then you can use the conversion, which is up at the top of the page here, 125 meters equals 1 inch, to convert them to x and y meters, and then you got to work backwards. So notice this way, with the theoretical, you work for x and y. Over here, you're going to take x and y and produce the radius vectors, and then the sum again. And that those two tables you'll then copy and paste into your lab report. Okay, I'm going to put measured right here. M-E-A-S, MES. All right, so that's that. And we're almost done. Just seconds away. All right. And you know, if you ever have any questions, you could sort of email me after I get home, after teaching, till 3:15. What is it, 3:15? 12:30, 1:30, 2:33. Yeah, about 3:15 I'll be out of there. Okay? I believe we're basically done. Let me just bring up the document again, the lab document. All right, so you got that, and then you got to find that you got to measure the distance between the two heads of the resultant vectors to find the delta r. You can just use your coordinates and do the distance formula. That'll give it to you right there. All right, so this student actually worked a little bit harder. They still use the distance formula, but they subtracted all the x and y coordinates. They put the theoretical resultant vector in the bottom because that is 100% correct, and then determine the percentage. All right, and then you answer your conclusion, and don't forget to do the hypothesis and the accuracy and precision. It's just one experiment, one trial, so you're just evaluating that one experiment. So that's it. Lopes out. We'll see you tomorrow in lab. Take care. Good night.